Hey guys, tonight we are going to follow something so familiar that you almost never notice it, even though it is touching you right this second. Gravity is here in the quiet room, in the weight of the blanket, in the stillness of your cup on the table, in the way the floor keeps patiently meeting your feet. Somewhere outside, trees lean into the night, clouds move slowly above rooftops, and the whole planet turns beneath you with a calm confidence that is honestly a little dramatic for something so silent. Before you get cozy, take a moment to like the video and subscribe, but only if you genuinely enjoy spending time here with me. And if you feel like leaving a tiny marker in this wide world, post your location and your local time in the comments so we can imagine all these little pockets of night happening together. Let the world slow down for a moment. Let the fan murmur softly nearby, and let's slip into tonight's journey together. The first relaxing thing about gravity is that it does not need your attention to work. You do not have to remember it, negotiate with it, or update it like an app that somehow needs permission to exist. It is already here, steady and continuous, doing one of the oldest jobs in the universe without making a sound. Gravity is the background music of being alive. Your body has known it since before you had words for anything. Your muscles grew with it. Your bones quietly shaped themselves against it. The water in your body settles under it. Every step you have ever taken has been a tiny conversation with the earth, a small rise, a soft return, a little promise that down will be there again. And down is not really a direction floating somewhere in space. Down is simply toward Earth's center, toward the heavy heart of the planet beneath you. Wherever someone is listening from tonight, whether they are in a bright city, a small town, a high apartment, or a quiet room near the sea, their down points inward into the same round world. Billions of people walking in different directions, sleeping on different sides of the globe, all held to the surface of a sphere by the same invisible pull. Gravity feels simple because it is constant in daily life, but the idea behind it is wonderfully deep. Anything with mass attracts anything else with mass. You pull on the earth, too, very gently, almost hilariously gently. The earth is so massive compared with you that your pull on it is too tiny to notice, but it is real. In the strict and quiet accounting of physics, you and the planet are attracting each other. Earth simply wins the visual argument, because Earth is enormous and you are, respectfully, more of a decorative detail. Still, that detail matters. Gravity is mutual. Everything leans toward everything else. A book rests on a nightstand because Earth pulls the book downward and the nightstand pushes back upward, firm enough to keep the book from continuing inward. Your sense of weight, that calm pressure against the bed or the chair beneath you, comes from that support. Gravity draws you toward the earth, and the surface gently answers. On Earth, gravity gives falling objects a speed increase of about 9.8 meters per second every second, when there is nothing in the way. That number sounds a bit like homework at first, so soften it into an image. If the air vanished and you dropped a small stone, it would fall faster and faster with every passing second, as though the planet were quietly inviting it home. In real life, air pushes back, surfaces interrupt the fall, and most of your day is not a physics problem screaming downward. Thankfully, that would be terrible interior design. Instead, gravity becomes comfort. It keeps your blanket settled around you. It keeps the lamp on the table. It keeps soup in a bowl, rain moving toward the ground, and rivers slowly remembering where the sea is. A hanging coat, a curtain, a sleeping cat, a plant bending slightly under its own leaves. All of them are quietly arranged by the same force. Gravity is also the reason Earth is round. A world as large as ours has enough mass for gravity to pull its material inward from every side. Over long stretches of time, rock and metal and ocean settle into a shape close to a sphere, because a sphere is the most even way for all that matter to gather around the center. The planet bulges slightly at the equator because it spins, but from far away, Earth still appears as a soft blue globe, a calm shape made by gravity and time. That same pull keeps the atmosphere close. The air around you does not simply wander away into space because Earth's gravity holds it near the surface. The oxygen you breathe, the drifting scent of rain, the small warmth of a room after sunset, all of it belongs to a thin, delicate layer wrapped around the planet. From space, that atmosphere would look almost impossibly slender, like a faint blue glow hugging the edge of the world. And here inside it, it feels wide enough for weather, birds, airplanes, clouds, and every quiet breath you take without thinking. There is something soothing about a force that works without hurry. Gravity gathers, it rounds, it settles, dust rests on a shelf. A loose strand of hair falls softly against your face. The moon remains near Earth because gravity holds it in a long, patient curve. We will wander closer to that moonlit rhythm later, so keep the image nearby. The same force that presses your pillow gently beneath your head also reaches across space with enough patience to guide another world around us. Gravity is weak compared with some of the other forces in nature, which sounds rude until you realize how quietly powerful weakness can become when it never gives up. A tiny fridge magnet can lift itself against the pull of the entire Earth. The whole planet is pulling downward, and a small magnet says, very politely, "I have plans." Yet gravity adds up. It reaches far. Give it enough matter and enough time, and gravity can build planets, stars, galaxies, and the great quiet architecture of the universe. In modern physics, gravity is often described as the curving of space-time, the way mass and energy shape the paths objects follow. That can sound enormous, and it is, but you can picture it gently. A heavy planet changes the geometry around it, and nearby objects move along those curves. So when you feel your body resting, you are feeling a local version of a cosmic truth. The same quiet pull that gathers worlds also steadies your hand on a blanket. There is one more gentle twist waiting just beyond this first comfort. The thing that gives you weight can also make weight disappear from your senses. An astronaut floating high above Earth is still deep inside Earth's gravity, still being pulled, still falling. The calm surprise is that everything nearby is falling together. Remember the feeling of the floor holding you up, because soon we are going to soften the idea of weight and discover why falling can sometimes feel like floating. The strange thing about gravity is that it can feel most peaceful at the exact moment it seems to vanish. Keep that earlier feeling nearby, the steady pressure of the bed, the floor, the chair, the quiet answer of the world beneath you. That feeling is what you call weight. It is so ordinary that your mind files it away with all the other background details of the room. The low hum of air, the faint shape of shadows, the small sounds that come and go without needing a name. But weight is not just gravity by itself. Weight is what you feel when something stops you from falling. That is a gentle little secret. When you stand on the ground, Earth pulls you inward and the ground pushes back. Your feet feel that upward support. Your body reads it as heaviness. The mattress beneath you, soft as it may be, is doing the same quiet job. It is preventing you from moving closer to Earth's center. And because of that, gravity becomes something you can feel through pressure. But remove that support, even for a moment, and the feeling changes completely. You have probably felt it in a small way before, maybe in an elevator that dips a little too quickly, or on a road where the car glides over a hill and your stomach rises with a tiny private complaint. For a second, you feel lighter. Your body has not escaped Earth. Gravity has not taken a coffee break, though honestly, after holding the moon for billions of years, it has earned one. What changes is the support beneath you. The surface pressing upward becomes weaker for a moment, and your body senses that softness as a brief floating feeling. Free fall is this feeling made pure. A falling object is still being pulled by gravity, but nothing is holding it up. A dropped pebble, a raindrop, a skydiver before air resistance becomes strong. All of them are following gravity's invitation downward. Inside that motion, something almost dreamlike happens. If you were falling beside a small object, the object would seem to hover near you, because both of you would be accelerating together. From your point of view, it would not feel like the object was dropping away. It would feel as if the normal heaviness had gone quiet. This is why astronauts float. It is one of the most relaxing misunderstandings in science, because the truth is more beautiful than the simple version. Astronauts on the International Space Station are not floating because there is no gravity up there. Earth's gravity is still very much present at that height. The station is only a few hundred kilometers above Earth's surface, which sounds far from your bedroom, of course, but compared with the size of the planet, it is like hovering just above the skin of an apple. Gravity there is still strong, only a little weaker than it is down here. The astronauts float because their spacecraft, their tools, their sleeping bags, their little packets of food, and occasionally a rogue crumb with suspicious confidence, are all falling around Earth together. Orbit is falling with sideways motion. The station moves forward so fast that as gravity pulls it downward, Earth's surface curves away beneath it. It keeps falling, and it keeps missing the ground. This sounds like a cosmic loophole, which it kind of is, and the universe appears to respect the paperwork. The result is a long, graceful fall that circles the planet again and again. Inside the station, there is no floor pushing up on the astronauts in the usual way. There is no steady support force telling their bodies, "Here is your weight." Everything shares the same falling path, so pencils drift, water forms floating beads, and hair spreads gently outward as if it has received artistic funding. The astronauts still have mass. They still have bodies that are difficult to move quickly. They are not weightless in the sense of becoming nothing. They are weightless in the sense that the familiar pressure of support has gone missing. That difference matters, and it is surprisingly calming. It reminds you that many sensations you think of as simple are really relationships. Weight is not only about the pull of Earth. It is about the conversation between pull and resistance, between gravity and the surface that answers it. Einstein found something profound hidden inside this idea. He noticed that being in free fall can make gravity seem to disappear locally. A person falling freely in a sealed elevator would float with nearby objects, unable for a moment to feel the pull that is guiding them. This became one of the clues leading toward general relativity, where gravity is understood less as a mysterious tug through empty space and more as the shape of spacetime itself. Matter tells spacetime how to curve, and moving things follow those curves. That may sound large enough to wake the whole room, so keep it gentle. Picture a quiet path shaped before you arrive. You move along it, not because someone is pushing you with a giant invisible hand, but because the landscape itself is curved. Gravity becomes less like a command and more like a direction that space has learned to whisper. And free fall is what happens when you are following that whisper without interruption. On Earth, air quickly makes falling less pure. A feather floats down slowly because air pushes against it. A stone falls faster because air has less time to slow it. In a vacuum, without air in the way, both would fall at the same rate. This was famously shown during the Apollo 15 mission on the Moon, where an astronaut dropped a hammer and a feather, and they reached the lunar surface together. It is such a quiet little experiment, almost childlike in its simplicity, yet it reveals something deep. Gravity gives the same acceleration to objects regardless of their mass, when air is removed from the story. There is something comforting about that fairness. Heavy or light, bright or dull, polished or dusty, everything receives the same calm instruction from gravity: fall together. Even falling itself does not have to be imagined as frantic. In space, falling can be smooth, endless, circular. The moon is falling around Earth. Earth is falling around the sun. The sun and all its planets move through the galaxy under gravity's wide influence. Everywhere, things are following curves. Everywhere, motion and falling blend so softly that the universe becomes a vast choreography of missing, circling, returning, and continuing. You can feel a small version of this whenever you toss something gently through the air. A ball does not travel in a straight line. It rises, slows, turns, and descends along a curve. That arc is gravity drawing it back. Throw it faster and it goes farther before returning. Imagine throwing it so fast that the ground keeps curving away beneath it, and you have the basic idea of orbit. A thrown object that never quite lands. A fall that becomes a path. This is why free fall feels like one of gravity's sweetest disguises. The force that holds you to Earth can also create floating rooms above it. The pull that makes your body feel heavy can, under the right motion, remove the feeling of heaviness altogether. Gravity does not disappear. It becomes shared. It becomes communal, almost polite. Everyone and everything falls together, so nobody feels singled out. There is a softness in that image. A spacecraft moving through night above the blue curve of Earth, its windows filled with clouds, oceans, thunderstorms flickering far below like silent lanterns. Inside, a sleeping astronaut is gently secured to the wall, because in orbit, a bed is more of a suggestion than a necessity. A small drop of water trembles in the air, round and shining, held together by surface tension, while gravity guides the whole station around the planet. And far below, the oceans answer another quiet pull. The same gravity that makes astronauts float in a shared fall also reaches across the space between Earth and Moon, lifting seas by a tiny amount spread over an enormous world. Keep that water bead in mind, round and shining in the cabin light, because soon the story widens from floating bodies to moving oceans, and gravity begins to look less like a downward force and more like a slow rhythm breathing through the planet. The water bead from that quiet spacecraft keeps shining for a moment, small and round in the cabin light, while far below it the oceans of Earth move in a much larger version of the same calm. Gravity is still there, always there, but here it stops feeling like a simple downward pull and begins to feel like rhythm. It becomes the slow lifting of the sea, the quiet return of water along a shore, the deep breathing of a planet that has been keeping time with the moon for longer than any human memory can reach. Stand beside the ocean in your mind for a while. It is night or close to night. The sand is cool. The waves arrive in patient lines, folding over themselves with that soft white sound that seems designed by the universe specifically for tired people. The water comes forward, pauses, and slips back again. It looks like the sea is making its own decisions, and in a small local way it is, shaped by wind, coastlines, seafloor storms, and the turning earth. But beneath all that restless surface detail, there is a deeper pull. The moon is lifting the ocean. Not lifting it like a hand lifting a bowl, of course. The moon is far away, about 384,000 kilometers from Earth on average, which is far enough that light takes a little over a second to make the trip. Still, the moon has mass, and mass attracts mass. Its gravity reaches Earth and gently tugs on everything: land, water, air, even you. The effect on your body is far too small to feel, so there is no need to blame the moon for your urge to open the fridge at midnight. That one may have other explanations. But across an ocean, where water can move and gather over huge distances, the moon's pull becomes visible. The tidal effect comes from a subtle difference. The side of Earth facing the moon feels the moon's gravity a little more strongly than Earth's center does, because it is slightly closer. The far side feels it a little less strongly, because it is slightly farther away. That small difference stretches Earth's oceans into two broad bulges, one roughly toward the moon and one on the opposite side. As Earth rotates through these bulges, many coastlines experience high tide and low tide in a repeating pattern. It is a beautiful thing to imagine. The planet turns, the moon circles, the water responds. No one is conducting it with a baton. No one is counting aloud. The rhythm simply emerges from gravity, motion, and time. The sun also helps shape the tides. It is much more massive than the moon, but it is also much farther away, so its tide-making effect on Earth is weaker than the moon's. When the sun, moon, and Earth line up during new moon or full moon, their tidal effects combine more strongly, creating spring tides. The name has nothing to do with the season. It comes from the idea of water springing higher. During first and third quarter moons, when the sun and moon pull at right angles from our point of view, the tides are more moderate. These are neap tides, quieter rises and falls in the long ocean breathing. Even that simple pattern becomes more interesting near real shores. Coastlines bend, bays narrow, the seafloor slopes, continents interrupt the motion. Because of this, tides do not arrive everywhere like a perfectly smooth wave wrapped around the globe. Some places have one strong high tide a day. Some have two. Some places barely notice the tide, while others see the ocean withdraw so far that boats rest in mud for a while, looking slightly embarrassed, then float again as if nothing happened. The Bay of Fundy in Canada is famous for some of the highest tides on Earth, where the shape of the bay helps amplify the water's rise and fall. In other places, tides spread gently across marshes, slide under mangroves, or lift seaweed along dark rocks. Small animals time their lives to this movement. Crabs, mussels, shorebirds, fish, and countless tiny creatures live by the schedule written between Earth and Moon. Gravity becomes a calendar. There is something calming about that. The tide does not hurry because you are watching. It does not adjust itself because a person has plans. It comes in at its own pace, under rules older than language. Long before clocks, people noticed these rhythms. They watched the moon change shape in the sky and the shoreline change shape below it. They learned when to fish, when to cross, when to gather, when to wait. The ocean became a clock with silver hands. And the moon's gravity does more than move water. It also pulls slightly on the solid Earth. The ground itself rises and falls by small amounts under tidal forces, too subtle for daily notice but real. Earth is not rigid in the absolute sense. It flexes. It answers. Beneath your feet, rock responds faintly to the moon and sun, swelling and settling with a grace too slow for ordinary senses. The planet is not a dead stone. It is a moving body, warm inside, turning, flexing, listening to gravity. Tides also affect the moon. This is where the story becomes even softer and stranger. Earth's gravity has slowed the moon's rotation over time until the moon became tidally locked. That is why the same side of the moon always faces Earth. It still rotates, but it rotates once in the same time it takes to orbit Earth, so the familiar near side remains turned toward us. The far side is not always dark, despite the old phrase. It receives sunlight just like the near side. It is simply hidden from direct view on Earth, a quiet face that waited for spacecraft to see it. That locking is not magic. It is gravity working over immense time, gently reshaping motion until rotation and orbit settle into a stable rhythm. The moon once spun differently. Over ages, tidal forces raised slight bulges in the moon's body, and gravity acted on those bulges, slowly changing the spin. The result is the calm, familiar face we see above rooftops and fields. The same pale markings watched by ancient travelers, night workers, poets, farmers, tired parents, and people standing at windows for no particular reason, except that the moon looked kind. Earth is changing too. The tides create friction as ocean water moves over seafloors and through coastal regions. That friction very slowly drains energy from Earth's rotation, making our days lengthen by tiny amounts over long spans of time. At the same time, the moon is slowly moving away from Earth by a few centimeters each year. That is about the speed your fingernails grow, which is a strangely intimate measurement for a celestial separation. The moon is leaving, but so slowly that the word leaving feels almost too dramatic. It is more like a long, quiet widening of distance. Keep that thought nearby. Gravity does not only hold things together, it also trades motion, shares energy, changes clocks, and stretches relationships across time. A tide pool under moonlight becomes a small mirror of the whole system. A thin pool between rocks may hold stars on its surface, while the real moon pulls on the sea beyond it. Tiny fish move in the shallow water. Shells gleam. Somewhere farther out, the ocean is rising by inches, then feet, depending on the coast. The entire scene is connected. The moon above, the turning Earth below, the water between them, and you nearby, breathing in air held by the same planet. The relaxing fact is not only that gravity makes tides, it is that tides reveal gravity as patience. Nothing about the ocean's rise needs to be sudden to be powerful. A small difference in pull, repeated across a whole world, becomes a rhythm strong enough to shape coastlines, guide animals, mark human time, and slowly change the length of a day. And this rhythm is only the beginning of a wider kind of motion. The moon does not simply pull on Earth's seas, it travels around Earth in a path shaped by gravity. Earth travels around the sun. The sun carries its family of planets through the galaxy. The tide at the shore, the floating astronaut, the cup resting on your table, all belong to the same graceful rule. Objects do not have to crash together to be connected. Sometimes they fall around one another for ages, holding distance like a promise, tracing curves through the dark with no need to arrive. Objects do not have to crash together to be connected. Sometimes they keep their distance with such grace that the distance itself becomes part of the relationship. The moon circles Earth. Earth circles the sun. Tiny satellites move above the night side of the planet, crossing oceans and deserts without touching them, held in motion by the same patient force that lifts tides and settles your blanket against you. An orbit is one of gravity's most beautiful tricks. It looks peaceful because it is balanced, but it is not still. Nothing in orbit is simply hanging there. The moon is moving, always moving, and Earth's gravity is always drawing it inward. The reason the moon does not fall straight down is that it also has sideways motion. It moves forward while Earth pulls it inward, and the result is a path that curves around the planet. A fall becomes a circle, or more accurately, an ellipse. A return that never quite becomes an arrival. That idea can feel strange until you picture a small stone thrown gently across a field. It rises, slows, curves downward and lands. Throw it faster and it travels farther before the ground catches it. Imagine the throw becoming so fast that the ground curves away beneath the stone at the same rate the stone falls. The stone would keep descending toward Earth, but Earth's surface would keep slipping away under it. That is the quiet heart of orbit, a continuous fall around a curved world. The International Space Station does this every day, moving at roughly 28,000 kilometers per hour. That number sounds absurdly fast, and it is. Yet from inside, motion can seem strangely calm. The station does not need rockets firing constantly to stay up, although small adjustments are needed over time because traces of atmosphere still reach that high and create drag. Mostly, it coasts. It falls around Earth in a wide, smooth path, circling the planet about every 90 minutes. Day, night, again and again, as Earth rolls below in blue and white silence. From the ground, a satellite may look like a tiny star sliding across the sky. No blinking lights, no engine roar, just a point of reflected sunlight moving with quiet purpose. It is easy to miss. It passes over rooftops, mountains, sleeping neighborhoods, dark forests, and wide black water. A little machine made by human hands, following a rule discovered by patient minds, held in a path by the pull of a planet that has no idea it is being useful for GPS, weather forecasts, and people trying to find the nearest coffee shop. Orbits can be close, wide, round, stretched, fast, slow, tilted, or carefully arranged. A low orbit moves quickly because the object is closer to Earth and gravity is stronger there. A higher orbit moves more slowly. Farther out, some satellites sit in geostationary orbit, high above the equator, taking one full day to circle Earth. From the ground, they appear to hover over the same region, which is why they are so useful for communication and weather watching. They are not fixed in space. They are moving with Earth's rotation in a perfect slow partnership. That kind of orbit feels almost poetic. A satellite turns at just the right pace, Earth turns beneath it, and the two stay face to face across thousands of kilometers. It is a quiet agreement made from speed, height, and gravity. Change one part too much and the agreement shifts. The planets are doing the same thing around the Sun, on a much grander scale. Earth moves around the Sun at about 30 kilometers each second, fast enough to cross a city in a blink. And still the ride feels motionless because everything nearby shares the journey. Your room, the trees outside, the ocean tide from earlier, the moon, the atmosphere, all of it travels together. You do not feel Earth racing along its orbit because there is no cosmic wind rushing past your face. Space is not a highway with air pushing at the windshield. The whole Earth moves as one steady vessel through the Sun's gravity. The Sun pulls on Earth, and Earth moves sideways fast enough to keep circling. Mercury, closer in, travels faster because the Sun's gravity is stronger near it. Neptune, far away in the dimmer edges of the solar system, moves much more slowly, taking around 165 Earth years to complete one orbit. That means one Neptune year lasts longer than a human lifetime. Somewhere out there, sunlight is faint. The Sun is a bright star rather than a blazing disk, and gravity still keeps the path going, patient as ever. Johannes Kepler noticed that planets do not move in perfect circles around the Sun. Their paths are ellipses, slightly stretched circles with the Sun off-center. Later, Isaac Newton showed how the same rules that pull an apple downward can also explain the Moon's motion around Earth. The ordinary and the celestial became part of one story. A falling apple, a circling moon, a tide moving through a bay, all belonging to the same law. That is one of the great calming ideas in science. The universe may be enormous, but it is not random in every direction. Patterns repeat. Rules echo. The small can teach the large. Still, orbit is never just one object obeying another. Every pair of bodies actually moves around a shared center of mass, called a barycenter. Earth and the Moon both circle their common barycenter, though it lies inside Earth because Earth is much more massive. The Sun also wobbles slightly because the planets tug on it, especially giant Jupiter. The solar system is not a perfect clock with one motionless center and obedient little worlds. It is more like a slow dance of many masses, each one pulling, each one responding, the whole thing held together by gravity's long reach. Jupiter is especially majestic in that dance. It is so massive that its gravity shapes the paths of asteroids and comets, and its moons form a small system of their own. The four largest moons, Io, Europa, Ganymede, and Callisto, were seen by Galileo more than 4 centuries ago, and they are still circling out there like a tiny solar system around a giant world. Some of them are caught in orbital resonances, meaning their periods line up in repeating patterns. Io, Europa, and Ganymede keep time with one another, their gravity tugging and flexing them in a steady rhythm. This flexing helps warm their interiors, especially Io, which is volcanically active, and Europa, which may hide an ocean under its icy shell. There is comfort in the idea that gravity can create rhythm without sound. Worlds pull on worlds, and those pulls become timing, warmth, tides, motion, even the possibility of hidden seas. Nothing has to announce itself. The universe is full of quiet arrangements. And sometimes, gravity creates places of unusual balance. There are regions called Lagrange points where the gravity of two larger bodies and the motion of an orbiting object combine in a stable or semi-stable way. Spacecraft can use some of these places as calm observing posts. The James Webb Space Telescope, for example, works near a point called L2, far beyond the Moon from Earth's perspective, where it can keep the Sun, Earth, and Moon in roughly the same direction and gaze outward into deep space with its shield facing the warmth behind it. Even our most advanced telescopes benefit from gravity's geometry. They do not conquer the universe. They cooperate with it. That may be the softest truth about orbits. They are cooperation written in motion. Too slow and an object falls inward. Too fast and it may escape. At the right speed it stays near, moving forever along a curve shaped by another body's presence. Gravity does not freeze things in place. It gives them paths. Your own life is surrounded by these paths. The Moon's path brings phases to the sky. Earth's path brings seasons, because our planet's axis is tilted as it travels around the Sun. Satellites overhead help map storms, guide ships, carry messages, and watch the changing surface of the world. Farther out, planets continue their long circuits, each one keeping a different tempo in the solar system's quiet music. A cup rests beside you because Earth pulls it down. A tide rises because the Moon pulls the sea. A satellite crosses the sky because it is falling around the planet with just enough sideways speed. The same idea keeps returning in different forms, familiar and cosmic at once. And as those paths widen in the imagination, gravity begins to do more than guide motion. It begins shaping the worlds themselves. It decides how tightly a planet holds its air, how high a mountain can rise before its own weight pulls it down, how round a moon becomes after ages of inward settling. Follow the orbit outward a little longer, and every world starts to feel like a sculpture made by gravity, time, and silence. Follow that thought outward from the path of a world to the world itself, and gravity becomes less like an invisible string and more like a sculptor. It does not carve with sharp tools. It works slowly, with pressure, weight, collapse, and balance. It rounds planets. It gathers oceans. It pulls mountains downward after they have tried their best to be dramatic. It decides whether a world can hold an atmosphere, whether dust becomes a moon, whether a tiny asteroid stays jagged and irregular or grows into something smooth enough to look peaceful from far away. You can picture Earth from space again, blue and white and softly curved, but this time the curve itself matters. Earth is round because gravity has had enough time and enough material to pull the planet inward from every direction. Rock is strong on human timescales. A cliff can stand for centuries. A mountain can rise for millions of years, but give gravity deep time, and even rock behaves less like a wall and more like something that can slowly yield. A large enough body settles toward a sphere because every part is pulled toward the center, and the most balanced shape is round. Small asteroids do not always have enough gravity to smooth themselves out. That is why many of them look like potatoes that have been through a lot emotionally. They can remain lumpy, stretched, dented, and odd because their self-gravity is too weak to overcome the strength of their materials. But when a body grows large enough, gravity begins to win. The roughness softens. The shape becomes more even. The object becomes a world. There is something comforting in that. Roundness in the universe is often a sign of patience. A planet is matter that has been gathered and pressed into calm. Gravity also decides how tall mountains can become. On Earth, mountains rise because tectonic plates push crust upward, but they cannot rise forever. The higher a mountain grows, the more weight its base must support. Rock deep below begins to deform under pressure and heat. Erosion works from above with rain, ice, wind, and time. Gravity pulls every slope downward, moving broken stone into valleys, rivers, plains, and eventually the sea. Even the tallest peaks are temporary gestures, held for a while in the long conversation between uplift and collapse. On a smaller world, mountains can grow much taller compared with the size of the planet, because gravity is weaker. Mars has Olympus Mons, a volcanic mountain so wide and high that it makes Earth's largest volcanoes seem modest, which is impressive, because volcanoes are not usually known for humility. Mars has only about a third of Earth's surface gravity, so giant structures can stand higher before their own weight becomes too much. The planet also lacks active plate tectonics like Earth's, so ancient volcanoes could keep building in place for immense stretches of time. On the Moon, gravity is weaker still, about 1/6 of Earth's. You would feel much lighter there, though your body would still have the same mass. You could hop in a slow, graceful arc, and each movement would take longer to return to the ground. Dust would rise and fall differently, without air to swirl it into clouds. Footprints left by astronauts remain sharply preserved because the Moon has no wind, no rain, and no flowing water to smooth them away. Gravity pulls the dust down, but almost nothing comes along to erase the quiet marks. That difference between mass and weight is worth holding gently. Your mass is the amount of matter in you. It stays the same whether you are on Earth, the Moon, or Mars. Your weight changes because weight depends on local gravity. On the Moon, you would weigh far less, but pushing a heavy object would still remind you that mass is real. It would resist changes in motion. Physics, very politely, would still keep receipts. Gravity also determines how a world holds air. A planet needs enough gravity to keep gas molecules from escaping easily into space. It also needs the right temperature, because hot gas moves faster. A small, warm world may struggle to hold a thick atmosphere. A larger or colder world may keep one more easily. Earth is in a fortunate balance. Its gravity is strong enough to hold nitrogen, oxygen, water vapor, and the other gases that make up the air, while still being gentle enough for mountains, birds, forests, and people walking around without feeling crushed. The Moon could not hold an atmosphere like Earth's for long. Its gravity is too weak, and gas molecules escape into space over time. Mars once had a thicker atmosphere, and evidence suggests liquid water flowed across its surface long ago. Today its atmosphere is thin, partly because Mars is smaller than Earth, with weaker gravity, and because it lost much of its global magnetic protection early in its history, allowing the solar wind to strip away atmospheric particles over long ages. The result is a cold, dry world of wide plains, ancient riverbeds, dust, and pale skies. Venus tells another story. Nearly the same size as Earth, with gravity only a little weaker, Venus holds a massive atmosphere. Its air is thick with carbon dioxide, and the pressure at the surface is immense. Clouds of sulfuric acid reflect sunlight above a world hidden beneath brightness. It is not a cozy place for a vacation, unless your travel agent is a toaster, but it shows how gravity is only one part of a planet's fate. Distance from the sun, chemistry, volcanic history, magnetic fields, and time all help write the atmosphere. Farther out, the giant planets show gravity at a grander scale. Jupiter has no solid surface like Earth's familiar ground. It is mostly hydrogen and helium, gathered into a vast sphere by enormous gravity. Deeper inside, pressure becomes extreme. The gas is compressed into strange states, including metallic hydrogen, where hydrogen behaves somewhat like an electrical conductor. Jupiter's gravity is strong enough to hold dozens of moons, shape rings, and influence countless smaller bodies around the solar system. It is a planet so massive that it is almost a tiny system of its own. And yet even Jupiter is shaped by balance. It spins quickly, so it bulges at the equator. Earth does this too, but more gently. A rotating planet is not a perfect sphere. Its middle widens slightly as the spin pushes material outward, while gravity pulls everything inward. The final shape becomes a quiet compromise between rotation and attraction. From far away, that compromise looks smooth and calm. Gravity shapes oceans as well as rock and air. On Earth, sea level follows an invisible surface called the geoid, shaped by gravity's small variations across the planet. Mountains, deep ocean trenches, dense rock below the crust, and the planet's rotation all affect how gravity is distributed. The ocean surface, if undisturbed by wind and currents, would follow this uneven gravitational shape. So even something that looks flat and simple, a wide ocean under a pale sky, is gently molded by hidden mass beneath it. Your own body belongs to this shaped world. The fluid in your inner ear helps you sense balance because gravity gives your nervous system a direction. Your bones stay strong partly because they bear weight. Plants grow with gravity as a guide. Roots usually grow downward, shoots upward. Life has learned the planets pull so deeply that it feels ordinary. Every tree trunk, every standing animal, every sleeping body has been designed in conversation with gravity. A world is not only a place where gravity happens. A world is what gravity makes possible. It gathers the material, presses it into shape, holds the air, guides the water, limits the mountains, and gives living things a steady downward direction to trust. It turns scattered matter into landscapes. And beyond these landscapes, gravity keeps gathering. The same patient force that rounds planets and holds atmospheres also reaches into cold clouds of gas and dust between the stars. In those dark, quiet places, where there is no shore and no mountain and no weather yet, gravity begins another kind of work. It draws faint material inward until the center grows warm, then hot, then brilliant. A planet is gravity's sculpture, but a star is gravity learning how to glow. A planet is gravity's sculpture, but a star is gravity learning how to glow. Beyond the shaped worlds, beyond the mountains that cannot rise forever, beyond the oceans held close to Earth and the thin blue air wrapped around it, there are places in space that look almost empty at first. They are cold, dim clouds of gas and dust, spread across distances so large that a human mind can only approach them slowly. From far away, they may look like faint mist between stars, a kind of cosmic breath resting in the dark. But inside that mist, gravity is working quietly. These clouds are made mostly of hydrogen, with helium and tiny grains of dust mixed in. They can be enormous, many light years across, wide enough to hold the raw material for thousands of stars. At first, everything is thin and cold. Particles move slowly. The cloud may seem calm, almost still, but stillness in space is often only the surface of a longer story. A passing shock wave from an old supernova, the pull of a nearby cloud, or the slow weight of the cloud's own material can begin to make one region a little denser than the rest. That tiny increase matters. A denser patch has slightly stronger gravity. It pulls in more material. More material makes it denser still. The process feeds itself, softly at first, then with growing purpose. Gravity gathers the cloud inward, not in a hurry, not with noise, but with the deep patience of a force that has never needed applause. As the gas falls inward, the center of the collapsing region becomes hotter. This happens because gravitational energy is being converted into heat. You can picture countless particles moving closer together, bumping more often, crowding into a smaller space. The newborn object is called a protostar. It is not yet a true star, but it is getting warmer, brighter, and more organized. Around it, leftover material may form a rotating disk, a flat whirl of gas and dust that can later become planets, moons, asteroids, and comets. So before a solar system has worlds, it has a kind of glowing cradle, a young star in the middle, a disk around it, dust grains sticking together in tiny collisions, pebbles becoming rocks, rocks becoming larger bodies. Gravity keeps gathering, sorting, shaping. The same quiet force that rounds planets begins by building the star they will orbit. A star truly begins when its core becomes hot and dense enough for nuclear fusion. Hydrogen nuclei combine to form helium, releasing energy. This is the light that reaches across space. It is the warmth on your skin during the day, the glow that makes leaves green, the energy that drives weather, oceans, and almost every living system on Earth. Sunlight begins in the sun's core, where gravity has squeezed matter so tightly that fusion can happen. This is one of the gentlest facts about stars once you hear it the right way. A star is not simply burning like wood in a fire. It is holding itself in balance. Gravity pulls inward, trying to compress the star. Fusion in the core releases energy, creating pressure that pushes outward. The star lives between those two tendencies. Inward pull, outward pressure. A long, luminous pause. The sun has been in that balance for about 4.6 billion years. It is middle-aged, steady, and thankfully not dramatic in the way some stars are. Every second, it turns a small amount of mass into energy, following the famous relationship between mass and energy described by Einstein. The numbers are huge, but the meaning can stay simple. Deep in the sun, matter becomes light. Gravity makes the conditions possible, and the result is morning, warmth, shadows on walls, fruit ripening on branches, and the soft gold of late afternoon. The light that leaves the sun's surface reaches Earth in about 8 minutes, but the energy created in the core takes far longer to reach the surface. Photons bounce through the dense solar interior in a slow, wandering path, absorbed and re-emitted again and again. They do not simply fly straight out. Their journey outward can take thousands of years, possibly much longer depending on how the path is described. Then, after all that hidden wandering, the final stretch to Earth takes only minutes. A patch of sunlight on your hand may have begun as energy in the sun's deep interior long before any person alive today was born. There is calm in that delay. Light is fast, but stars are patient. Gravity also decides what kind of star a cloud can become. A smaller star burns its fuel slowly and can shine for an incredibly long time. Red dwarfs, the most common stars in the galaxy, are small, cool, and long-lived. Some may last for trillions of years, far longer than the current age of the universe. They are not showy. They glow modestly, quietly, like the universe's low lamps. Massive stars live differently. Their greater gravity squeezes their cores harder, making fusion happen faster and more intensely. They shine brightly, sometimes with blue-white brilliance, but they spend their fuel quickly. A massive star may live only millions of years, which sounds long until you compare it with the sun's billions. In the universe, brightness often comes with a shorter clock. Even stars, apparently, have to manage their energy budget, relatable in a cosmic and slightly unfair way. Inside stars, gravity creates layers of transformation. In stars like the Sun, hydrogen fuses into helium. In more massive stars, later stages can fuse heavier elements, building carbon, oxygen, neon, silicon, and eventually iron in their cores. Elements that make up planets and living things were forged in stars or created in the powerful events around their deaths. The calcium in bones, the oxygen in your breath, the iron in blood, the carbon in every cell, all belong to a cosmic history shaped by gravity and nuclear fire. That does not need to feel overwhelming. It can feel tender. Your body is not separate from the universe looking out at it from a distance. It is made from material that stars helped prepare. Gravity gathered the stars. Stars made elements. Those elements spread into space and later gathered again into new clouds, new suns, new planets, and eventually the soft, ordinary miracle of someone resting in a quiet room, listening to a story about gravity. Star clusters make that story even more beautiful. Many stars are born together from the same great cloud, like siblings of light. Some clusters remain loosely gathered, their stars drifting slowly apart over time. Others, called globular clusters, are dense and ancient, holding hundreds of thousands of stars in a round swarm around galaxies. Gravity binds them together for billions of years. From inside such a cluster, the night sky would be crowded with stars, bright in every direction, as if darkness had been embroidered with fire. Our own sun was probably born in a cluster too, though its siblings have long since scattered through the Milky Way. The star that warms Earth may have started life near other young stars, inside a cloud that has since thinned and vanished. Over time, gravity and motion carried those stars along different paths. The sun kept its planets, Earth cooled, oceans formed, life began. And through every stage, gravity remained in the background, gathering, balancing, holding. Even the shape of a star is gravity's work. A star is round because gravity pulls its material inward from all directions, while pressure supports it. Some stars spin so quickly that they bulge at the equator just as planets do. Some stars orbit in pairs, bound by each other's gravity, circling a shared center of mass. Binary stars are common. In some systems, one star may pull gas from another, drawing bright streams of material across space. Gravity can be gentle, but it is never idle. The sun itself is not perfectly still. It trembles with waves moving through its body. Scientists study those vibrations to learn about the solar interior, a field called heliosismology. The star rings softly in its own way, with patterns shaped by pressure and gravity. You cannot hear the sun across the vacuum of space, but the idea is beautiful. The star that lights your day has internal music. And all of this began with a cloud that was just a little denser in one place. That may be the quiet lesson hidden in starlight. Gravity does not always begin with grandeur. It begins with a difference so small it could be missed. A slight gathering, a faint inward motion, a cold cloud becoming a warm center becoming a star becoming the source of worlds. The same pull that settles dust on a shelf can, given enough distance and time, gather a sun from darkness. The same force that gives your body weight can build the light by which oceans shine. Gravity is humble at close range and magnificent at scale, which is a very impressive personality range for something that never speaks. Beyond individual stars, their light gathers into larger patterns. Billions of stars move together, held by gravity in immense islands called galaxies. Our sun is one star in one such island, the Milky Way, turning slowly with its neighbors around a center hidden by dust and distance. The architecture grows wider again. Stars become rivers. Rivers become spirals. And in the dark spaces between those spirals, another mystery waits, quiet and massive, guiding more than the eye can see. Stars become rivers. Rivers become spirals. And if you follow the soft architecture of stars far enough, the universe stops looking like a scatter of lights and begins to look like a vast, dark ocean filled with glowing islands. A galaxy is one of those islands. It is a city of stars, gas, dust, planets, old light, new light, and hidden mass, all gathered into a shape by gravity. Some galaxies are graceful spirals with arms curling outward like slow water. Some are smooth ellipses, glowing softly with older stars. Some are irregular, shaped by encounters, collisions, and long gravitational conversations with their neighbors. They look still in photographs, because the human eye catches them in one frozen moment, but they are moving all the time. The Milky Way, your home galaxy, is a barred spiral, which means its center has a long, bright bar of stars, with spiral arms winding outward from it. The Sun lives in one of those arms, far from the center, in a quieter stellar neighborhood. From Earth, you cannot step outside the Milky Way to admire it from a distance, which is rude, honestly, because the view would be excellent. Instead, you see it from within, as a pale band across a dark sky, where countless distant stars blend into a soft, cloudy glow. That glow is not a cloud in the usual sense. It is starlight gathered so densely and so far away that individual stars blur together. When you look toward the Milky Way on a clear night, you are looking through the flat disk of the galaxy itself, across dust lanes and star fields, toward a depth your eyes can sense before your mind can measure. It is like standing inside a cathedral and realizing the walls are made of suns. Gravity holds this whole structure together. The stars of the Milky Way orbit the galactic center, just as planets orbit the Sun, though the scale is far larger and the motion is slower. The Sun takes roughly 225 to 250 million years to complete one journey around the galaxy. One galactic year is so long that the last time the Sun was in this part of its orbit, dinosaurs walked Earth. Since then, continents have shifted, oceans have opened and narrowed, mountains have risen and worn down, and the Sun has simply continued along its wide path, carrying Earth with it like a small blue lantern. There is something deeply calming about that pace. Your day can feel full of little emergencies, small clocks, messages, appointments, errands, and cups of tea forgot until they become room temperature in a morally disappointing way. Meanwhile, the Sun is making a single slow turn around the galaxy, taking hundreds of millions of years to complete what gravity has drawn into a path. The universe is not rushing. It has never been rushing. But galaxies brought scientists a strange clue. When astronomers studied how stars move around the centers of spiral galaxies, they expected the outer stars to move more slowly, much like planets farther from the Sun orbit more slowly than planets closer in. In the solar system, Mercury moves quickly, Earth moves more gently, and distant Neptune takes its long, cold time. That pattern makes sense because most of the solar system's mass is concentrated in the Sun. Galaxies behave differently. The outer stars in many spiral galaxies were moving faster than expected, as if more gravity were present than the visible stars and gas could explain. The galaxies were turning as though they were embedded in much larger halos of unseen matter. This evidence, strengthened by the work of astronomers including Vera Rubin and Kent Ford, became one of the great signposts pointing toward dark matter. Dark matter does not glow. It does not absorb or reflect light in the ordinary way. It does not announce itself through a bright surface or a shining cloud. We infer it through gravity, through the way galaxies rotate, through the way clusters of galaxies hold together, and through the way light bends as it passes massive regions of space. It seems to make up much more of the universe's matter than the familiar atoms that build stars, planets, oceans, and your very considerate pillow. That can sound mysterious in a sharp way, but it can also feel peaceful. The universe is telling us there is more holding things together than what our eyes can see. Around each galaxy, there may be a broad, dark halo, an invisible gravitational presence extending far beyond the bright disk. The stars turn within it. Gas clouds move through it. The whole galaxy lives inside a deeper shape. You do not have to picture dark matter as a shadowy fog with edges you could touch. It is not simply darkness in the poetic sense. It is a name for something real that acts through gravity but remains unseen by light. Scientists do not yet know exactly what dark matter is made of. It may be some unknown kind of particle. It may require new understanding. The evidence for its gravitational effects is strong, while its nature remains one of the quiet open doors in modern science. And that open door is part of the beauty. Science does not become less calming because it has mysteries. It becomes more alive. A finished universe would be tidy, perhaps, but not nearly as spacious. Dark matter gives the cosmos a kind of soft depth. The stars are the visible embroidery. The hidden gravity is the fabric that helps hold the pattern. Galaxies also interact with one another. They do not float forever in perfect isolation. Gravity reaches across the dark between them, drawing them into groups and clusters. The Milky Way belongs to a small gathering called the Local Group, along with the Andromeda Galaxy, the Triangulum Galaxy, and many smaller galaxies. Andromeda is moving toward the Milky Way, and in several billion years the two great spirals are expected to merge. This will not be a sudden crash of stars like sparks colliding. Galaxies are mostly empty space, and stars are so far apart that direct stellar collisions would be rare. Instead, gravity will reshape the galaxies over immense time, stretching arms into streams, stirring stars into new paths, and eventually creating a larger, smoother galaxy. It is a magnificent thought, but not an urgent one. Billions of years stand between here and there. The night remains quiet. The Milky Way still turns. Andromeda still glows faintly in the sky for those who know where to look. The future waits at a scale so wide that it becomes almost restful. In galaxy clusters, gravity works on even larger stages. Hundreds or thousands of galaxies can gather together, bound by mutual attraction and dark matter. Between them lies hot gas, spread through the cluster, glowing in X-rays. The galaxies move like slow fish in a vast, invisible sea. The dark matter helps hold the cluster together, giving it more gravitational strength than visible matter alone could provide. Even clusters gather into filaments, long strands of galaxies and dark matter forming the cosmic web, the largest known structure in the universe. The cosmic web is one of the most beautiful ideas in modern astronomy. Matter is not spread evenly everywhere. Gravity has drawn it into a vast pattern of threads and nodes, with enormous voids between them. Galaxies line the filaments like dew on spider silk. Clusters shine at the intersections. Between those structures stretch regions so empty and wide that they make even galaxies seem delicate. And through all of it, gravity is the patient organizer. It amplifies tiny differences from the early universe. A region just slightly denser than another pulls in a little more matter. That matter strengthens the pull. Over billions of years, the faintest unevenness grows into stars, galaxies, clusters, and the cosmic web. The grandeur begins in almost nothing. A tiny variation, a small excess of density, a gentle imbalance given time. Keep that image close. Bright galaxies turning inside invisible halos, clusters held by hidden gravity, long filaments crossing the dark. The universe is not only filled with light, it is shaped by what light cannot reveal directly. And soon, even light itself will become part of gravity's story, because when it passes near something massive enough, its path bends. The darkness does not merely hold the stars. It can curve the journey of starlight, turning space into a lens, and distant galaxies into soft arcs and rings across the night. The darkness does not merely hold the stars. It can curve the journey of starlight itself, and that is where gravity becomes almost unbelievably quiet in its elegance. Light feels like the freest thing in the universe. It crosses empty space at the fastest speed anything can travel. It leaves a star, slips between worlds, glides through the dark, and reaches your eye as a tiny messenger from somewhere far away. A beam of sunlight through a curtain seems weightless, gentle, impossible to catch. You can hold your hand inside it and feel warmth, but the light itself keeps moving, touching dust in the air and then continuing on, as if it has no reason to pause. Yet even light follows the shape of space. When something massive sits in the universe, it curves spacetime around itself. A planet does this a little. A star does it more. A galaxy cluster does it enormously. Light passing nearby does not bend because it is being grabbed like a thrown object with a string attached. It bends because the path through space has changed. The road itself is curved, so the traveler follows the curve. This is one of the most beautiful ideas in gravity. Space is not simply an empty stage where the universe performs. Space has shape. Time is part of that shape. Matter and energy tell space-time how to curve, and light moves through that curved geometry with perfect obedience, though obedience may be the wrong mood for something as graceful as starlight. It is more like light is reading the landscape at full speed. A simple way to picture it is to imagine crossing a wide valley. If the valley floor dips gently, your path changes with the land. You are still walking forward, but the ground gives your motion a shape. In the universe, massive objects create a kind of valley in space-time, and light passes through the changing geometry. The result is gravitational lensing, one of the calmest and most magnificent effects in all of astronomy. A gravitational lens can magnify and distort light from objects far behind it. If a massive galaxy or cluster lies between Earth and a more distant galaxy, the gravity of the nearer object can bend the distant galaxy's light around it. From Earth, that far galaxy may appear stretched into arcs, doubled into multiple images, or even wrapped into a near-perfect ring called an Einstein ring. The original galaxy may be so distant that, without the lens, its light would be too faint to study clearly. Gravity becomes a telescope made of space-time. This is especially soothing because nothing is touching anything. A galaxy cluster may sit quietly in the foreground, hundreds of billions or even trillions of stars held together with dark matter and hot gas. Far behind it, another galaxy sends light across the universe. That light travels for billions of years, reaches the curved space-time around the cluster, and gently changes direction. Eventually, a telescope near Earth catches it. A scene separated by almost unimaginable distance becomes visible because gravity quietly folded the path. Some of the most beautiful space images show blue or golden arcs around galaxy clusters. Those arcs are distant galaxies, stretched by lensing into delicate curves. They look like brushstrokes around islands of light. Each arc is a real object, often far behind the cluster, and its strange shape is a clue. By studying these distortions, astronomers can map where mass is located, including dark matter that cannot be seen directly. The visible galaxies are only part of the story. The bending of light reveals the hidden weight around them. So gravity, which once felt like the pressure of a blanket and the steadiness of a floor, becomes a way to see the unseen. It shows itself through motion, through tides, through orbits, through the shape of worlds, and here through the bending of light. It never needs to glow to be known. It leaves signatures in the paths things take. The sun bends light too. During a solar eclipse in 1919, astronomers measured starlight passing near the sun and found that the apparent positions of stars shifted by the amount predicted by Einstein's general relativity. The stars were still far behind the sun, but the sun's gravity curved the light on its way to Earth. This observation helped make Einstein famous, though the stars themselves were probably very calm about it. They had been sending light the whole time, with no concern for human headlines. The effect near the sun is small but real. Near larger masses, it becomes more dramatic. Galaxy clusters act as powerful lenses because their combined mass is enormous. Even a single galaxy can lens a more distant object. Sometimes a bright quasar, the glowing core of a distant galaxy powered by a supermassive black hole, appears as multiple points of light because a nearer galaxy bends its light into several paths toward us. The same object reaches us through different routes, like one voice arriving through several quiet doorways. Those routes can have different lengths, so the light may arrive at slightly different times. If the distant object changes in brightness, astronomers may see the change first in one image, then later in another. Gravity has created a natural delay, a cosmic echo carried by light. Time, distance, and curvature become braided together. There is also a softer, more widespread version called weak gravitational lensing. It does not create obvious arcs or rings. Instead, it slightly distorts the shapes of many background galaxies. By measuring many tiny distortions across the sky, scientists can trace the large-scale distribution of mass in the universe. It is a patient kind of seeing. No single galaxy shouts the answer. Many small shapes whisper it together. That feels appropriate for gravity. It often speaks through accumulation. One falling object, one tide, one orbit, one curve of light. Then many of them together reveal the pattern. The phrase bending light can sound like magic, but the reality is more satisfying than magic because it is lawful. A photon, a particle of light, has no rest mass, but it still carries energy and momentum, and it travels through space-time. Since gravity is the curvature of space-time, light follows that curvature. The old idea of gravity as a simple pull becomes something wider and calmer. The universe has geometry, and light traces it. You can imagine a beam from an ancient galaxy beginning its journey before Earth had complex life, before flowers, before birds, before human eyes. It crosses an expanding universe, passing through darkness so wide that whole civilizations could rise and vanish in less than a blink of its travel time. Near the end of the journey, it brushes past a cluster of galaxies. Space curves. The beam divides into several possible paths. A telescope catches the light, and on a screen it appears as a faint arc, a smudge, a glow, a clue. Somewhere, a scientist studies that clue. Somewhere else, you rest beneath the same gravity that shaped the path. The scale changes, but the force remains connected. The weight of your body and the bending of ancient starlight belong to the same story. And deeper still, there are places where the curvature becomes so strong that light does more than bend. It can circle. It can struggle. It can approach a boundary beyond which no signal returns to the outside universe. These places do not need to be treated with fear. They are among the most mysterious and strangely elegant objects gravity can create. After seeing light curve like a dream, the path leads naturally toward the calm edge of black holes, where gravity becomes so deep that even time seems to lower its voice. After seeing light curve like a dream, the path naturally deepens toward the places where gravity becomes so strong that even light cannot return to the outside universe. Black holes can sound intense at first, mostly because the name is doing absolutely nothing to be charming. It sounds like something a dramatic villain would keep in a basement. But in the quiet language of physics, a black hole is simply a region where gravity has curved spacetime so deeply that every future path inside a certain boundary points inward. That boundary is called the event horizon. It is not a solid surface. You would not see a wall there, or a shell, or some dark glass edge hanging in space. It is more like a one-way line in the geometry of the universe. Outside it, light can still move away if it has the right path. Inside it, all paths lead deeper. The event horizon is the point where escape is no longer part of the map. There is a strange calm in that idea, if you hold it gently. A black hole is not reaching across the universe like a cosmic vacuum cleaner, chasing stars around with poor manners. Far away from a black hole, its gravity behaves like the gravity of any other object with the same mass. If the Sun could somehow be replaced by a black hole of equal mass, Earth would continue orbiting at the same distance, though of course the missing sunlight would be a rather serious customer service issue. The orbit depends on mass and distance. The black hole does not become magically greedy just because it is compact. What makes a black hole special is not that it has infinite reach. Gravity already reaches across space in every direction. What makes it special is how much mass is packed into such a small region. When enough matter collapses inward, no known pressure can stop the formation of an event horizon. The spacetime around it becomes deeply curved, and the ordinary rules of distance and time begin to behave in ways that feel almost dreamlike. Some black holes are born from massive stars. A large star spends its life balancing gravity against the pressure created by fusion in its core. When its fuel runs low and the inner support changes, gravity can take over. The outer layers may be thrown outward in a brilliant stellar explosion, while the core collapses. If the remaining core is massive enough, it can become a black hole. A star that once shone across space leaves behind a place where gravity has gathered the story inward. Other black holes are enormous, millions or billions of times the mass of the Sun. These supermassive black holes sit at the centers of many large galaxies, including the Milky Way. Ours is called Sagittarius, a compact, quiet heavyweight at the heart of the galaxy, surrounded by stars that orbit it at extraordinary speeds. Those stellar orbits reveal its presence, even though the black hole itself does not shine. Once again, gravity leaves its signature through motion. Black holes themselves are dark, but the space around them can be bright. Gas and dust falling toward a black hole may form an accretion disk, a flattened whirlpool of material heated by friction and intense gravity until it glows. These disks can become some of the most luminous structures in the universe, especially around supermassive black holes feeding in the centers of distant galaxies. The darkness at the center is surrounded by light made from matter moving at breathtaking speed. It is a quiet reminder that gravity can hide and reveal at the same time. A black hole also changes time. According to general relativity, time passes differently depending on gravity and motion. Near a massive object, clocks tick more slowly compared with clocks far away. Near a black hole, this effect becomes dramatic. To a distant observer, something falling toward the event horizon would appear to slow and fade, its light stretched toward redder wavelengths. From the falling object's own point of view, time would continue normally for a while, because every traveler carries their own local clock. That difference is one of the softest mysteries in physics. Time is not one universal river flowing at the same pace everywhere. It can be shaped by gravity. A clock near Earth ticks very slightly differently from a clock high above it, and this has to be accounted for in technologies like GPS. Near a black hole, the same principle becomes grand and strange. Gravity does not only curve space, it folds time into the story. There is also a region near a black hole where light can orbit, called the photon sphere. For a non-rotating black hole, this lies outside the event horizon. Light there can circle the black hole, though the orbit is unstable. A tiny disturbance sends the light inward or outward. It is a beautiful, delicate image, light itself tracing a temporary ring around gravity's deepest well, like a bright thought unable to decide whether to stay. Real black holes often rotate because the stars and gas that created them had spin. A rotating black hole drags spacetime around with it, an effect called frame dragging. This means the geometry nearby is not simply curved inward, it is stirred. Space and time are pulled into motion around the spinning object. The universe in that region behaves almost like silk twisting around a hidden center. And still, from far away, it can all look peaceful. A black hole in the center of a galaxy may sit in darkness while stars circle around it for millions of years. It does not need to announce itself. It does not have to glow. Its gravity shapes the movement of nearby stars, the flow of gas, the rhythm of the galactic center. Quiet influence is still influence. Scientists have even seen the shadow of black holes, or more precisely, images of the glowing material around them shaped by strong gravity. The Event Horizon Telescope created images of the supermassive black hole in the galaxy M87 and later Sagittarius A/. These images do not show the black hole's surface because there is no surface to see. They show a bright ring of emission around a dark central region where light paths are bent and captured. It is as close as humanity has come to photographing gravity's deep silence. The idea of a black hole shadow is wonderfully poetic because the shadow is not made by blocking light in the ordinary way. It is made by light failing to return. Around it, photons curve, swirl, escape, or vanish inward. The image becomes a portrait of paths. Some paths reach us, some do not. Black holes also whisper through gravitational waves. When two black holes orbit each other and merge, they send ripples through spacetime itself. These waves travel across the universe at the speed of light, stretching and squeezing space by incredibly tiny amounts as they pass. Detectors on Earth have measured them, catching the faint after-ripple of distant mergers. No sound travels through the vacuum between galaxies, but spacetime can carry a kind of silent ringing from one of the most powerful events nature allows. Even here, the mood can stay calm. A gravitational wave reaching Earth after traveling for billions of years is unbelievably faint by the time it arrives. It passes through the planet like a ghost of geometry, leaving only the smallest measurable trace. Somewhere far away, two black holes became one. Long afterward, Earth received the quiet signature. The deeper you follow gravity, the more it seems to turn from force into shape, from shape into time, from time into mystery. Black holes sit at the edge of what current physics can describe. General relativity explains the event horizon and the curved spacetime around it beautifully. Quantum physics works wonderfully on tiny scales. But at the center of a black hole, where theory points toward a singularity, our understanding becomes incomplete. That is not a failure in the story. It is an honest doorway. The universe still has rooms we have not learned how to enter. And maybe that is part of why black holes can feel strangely peaceful tonight. They are not only symbols of darkness. They are reminders that gravity has depth beyond ordinary experience. The same pull that gives weight to your body can bend light, slow time, make stars orbit invisible centers, and send ripples through space-time after distant mergers. The familiar and the mysterious are connected by one continuous thread. From the floor beneath you to the moon's tides, from planets to stars, from galaxies to black holes, gravity has been gathering the journey into wider and quieter forms. Beyond even these deep places, the story opens into time itself. The future of stars, the spreading of galaxies, the long patience of matter as the universe continues changing. Gravity does not rush that future. It holds, shapes, releases, gathers again, and carries everything forward with the slow calm of something that has always known how to wait. Gravity does not rush that future. It holds, shapes, releases, gathers again, and carries everything forward with the slow calm of something that has always known how to wait. After black holes, after the bending of light and the quiet slowing of time, it may feel as if gravity has shown its deepest face. But gravity is not only about the dramatic places where spacetime folds sharply. It is also the patient keeper of ordinary futures. It works in the long spaces between events. It guides dust after explosions, gathers gas after stars fade, and keeps galaxies arranged in patterns so wide that even light needs millions of years to cross them. The future of the universe is not written like a fast story. It is written like frost forming on glass, like mountains wearing down grain by grain, like a tide returning over and over until the shoreline itself begins to change. Gravity is one of the forces that gives that future shape. The sun, for now, is steady. It has been shining for about 4.6 billion years, and it still has billions of years left in its current calm middle age. Deep in its core, hydrogen becomes helium, energy moves outward, and Earth receives sunlight after that final 8-minute journey across space. One day, far in the future, the sun will change. It will use up much of the hydrogen in its core, expand into a red giant, shed its outer layers, and leave behind a white dwarf, a small, dense remnant slowly cooling in space. That future is far beyond the scale of human nights. It is not something pressing against this room. It is simply part of the long life of stars. Gravity will be there through each stage. It will help the sun hold its shape while fusion continues. It will pull the remaining core inward when the outer layers drift away. It will keep the white dwarf compact, dense, and slowly fading. A white dwarf is not a star like the sun anymore, but it still carries the memory of one. It is about the size of Earth, yet with a mass closer to the sun's, packed tightly into a small sphere. It glows from leftover heat, cooling across immense time. No flame in the ordinary sense. No fresh fusion in its core, just stored warmth leaking slowly into the dark. It is a quiet ember of a former sun. Other stars have different endings. Smaller stars may burn gently for astonishing lengths of time. Red dwarfs can shine so slowly and efficiently that many may last for trillions of years. The universe is not even old enough yet for the smallest red dwarfs to have finished their lives. They are still in their early chapters, glowing patiently in the dark, spending their fuel with almost absurd discipline. Honestly, some of us could learn from that energy management. Massive stars live faster. Their gravity squeezes their cores more strongly, their fusion runs fiercely, and their lives end in powerful collapses. Some leave neutron stars, objects so dense that a spoonful of their material would have an almost unimaginable mass. Some leave black holes. Some spread heavy elements into space, enriching future clouds with the ingredients for planets and life. Gravity gathers a star. The star makes elements. Gravity helps the star die, and the released material becomes part of the next beginning. So gravity is not only a force of endings, it is also a force of recycling. It makes return possible. A cloud of gas and dust may drift for ages after being enriched by old stars. Slowly, one region becomes denser. Gravity notices, as gravity always does. The region pulls in more material, warms, collapses, and perhaps a new star forms. Around it, a disk may flatten and swirl. Dust grains meet, pebbles grow, rocks gather, worlds begin again. In this way, the universe feels less like a straight road and more like a long breathing cycle. Stars gather and shine. They fade, shed, collapse, or explode. Their material returns to space. New stars rise from old remains. Planets form from the dust of previous generations. Every rocky world is built from something that came before. Earth itself is part of that inheritance. The atoms in its crust, oceans, atmosphere, and living things were not made all at once in one place. Hydrogen came from the early universe. Heavier elements were formed in stars and stellar explosions, or in powerful cosmic events. Gravity helped gather those materials into the cloud that became the sun and planets. And here you are, made of that history, resting inside it, hearing about it through a body assembled from ancient matter. There is something quietly magnificent about being held by Earth while also being made from older stars. Gravity is not just beneath you, it is in your story. On larger scales, galaxies will keep changing. The Milky Way and Andromeda are moving toward one another, and in several billion years they are expected to merge. The word collision can make it sound loud and crowded, but galaxies are mostly space. Their stars are separated by enormous distances. The merger will be a long gravitational reshaping, a slow folding of two stellar islands into one larger structure. Spiral arms may stretch into streams. Stars may be thrown onto new paths. Gas may compress and form new stars. Over time, the combined galaxy may settle into a smoother shape. Gravity will not make that happen in a single moment. It will take ages. The first approach, the long passage, the tidal stretching, the returning arcs, the final settling. It will be more like ink moving through water than stones smashing together. Vast, slow, silent, and beautiful. Farther out, galaxies belong to clusters. Clusters belong to filaments, and the cosmic web continues to evolve. The universe is expanding, and on the largest scales, that expansion carries distant galaxy groups away from one another. Gravity gathers matter locally, while the expansion of space stretches the distances between great structures. The future becomes a balance between what gravity can hold and what expansion carries beyond reach. Some galaxies will remain bound together in groups. Others, far beyond, will drift out of view as space expands between them and us. Light from the most distant regions will become harder to receive. The night sky of the far future may grow emptier for any beings looking outward from some quiet world. Their local stars may still shine. Their galaxy may still glow, but the wider universe may hide behind distance and time. That thought could feel lonely, but tonight it can be softened. Every age of the universe has its own beauty. The early universe was hot and bright. Later came the first stars. Then galaxies grew, planets formed, chemistry deepened, and life appeared in at least one small place under one yellow-white star. The far future will have its own silence, its own embers, its own long cooling light. Gravity will remain part of that silence, gathering what can still be gathered, holding what can still be held. Even black holes are not perfectly final in our best current understanding. According to quantum theory, black holes may slowly lose energy through Hawking radiation, an effect so faint for large black holes that it would take unimaginable lengths of time to matter. But over vast futures, black holes may slowly shrink and fade. This is not something anyone will observe in an ordinary human timescale. It belongs to time so deep that language begins to feel small. Still, it suggests that even the darkest gravitational places may have an ending, eventually, softly, after almost everything else has gone quiet. And through all of this, gravity remains the thread. It begins in your room as weight. It becomes the fall of a pebble, the drift of an astronaut, the tide under moonlight, the orbit of planets, the shaping of worlds, the birth of stars, the turning of galaxies, the bending of light, the edge of black holes, and the long future of matter itself. The comfort is that all these scales are connected. You do not need to hold them all at once. You can feel just one, the steady support beneath you. That is enough. The same universe that builds galaxies also allows a cup to rest on a table. The same geometry that bends ancient starlight also gives your body a place to be. Gravity is often described as a force, but tonight it has felt more like a form of trust. It keeps the moon near. It keeps the air close. It gives oceans rhythm, planets paths, stars their glowing balance. It turns scattered dust into worlds and turns worlds into homes. It lets the universe have structure, memory, and return. So the most relaxing fact about gravity may be this: it is always making belonging possible. Matter belongs to matter. Worlds belong to stars. Moons belong to planets. Light belongs to the curves it travels. And for this quiet moment, you belong to the earth beneath you, held without effort, without noise, without needing to understand every equation. The universe is vast, but it is not indifferent in the way empty space first appears. It is full of relationships, pulls, curves, rhythms, shared motion, silent agreements. Even distance does not erase connection. The moon lifts the sea from far away. The sun holds Earth in a wide, bright path. Galaxies tug on neighbors across darkness. Gravity speaks softly across emptiness, saying in its own wordless way, stay near, move gently, keep going. And here, near the end of the journey, the scale can come back down. From galaxies to stars, from stars to planets, from planets to oceans, from oceans to one room, one body, one breath. Gravity is still here. It has been here the entire time. It was here before you noticed it, and it will remain after the thought fades. The blanket still has weight, the floor is still steady, the air is still held close to Earth. Somewhere the ocean is rising by moonlight. Somewhere a satellite is falling around the planet without landing. Somewhere starlight bends around a distant galaxy. Somewhere a quiet white dwarf cools. Somewhere a dark cloud begins to gather itself into a future sun. And all of it belongs to the same slow story. The room can become simple again. The great distances can soften and drift away, leaving only the nearest comforts. A breath in, a breath out, the gentle pressure of the world holding you in place. The quiet knowledge that nothing needs to be chased right now. Gravity has everything it needs. The earth is doing its old work beneath you. The moon is keeping its pale path. The stars continue with their patient fires. You do not have to carry the universe tonight. It is already carrying you in the only way it knows how, through touch, through weight, through curved space, through a calm and ancient pull that never asks to be noticed. The night can widen without becoming heavy. It can simply open around you, soft at the edges, full of dark blue distance and tiny lights. Every thought can settle like dust in a quiet room. Every worry can loosen a little, the way a wave loosens its shape when it reaches the shore. There is no need to hurry towards sleep, no need to measure the moment, no need to solve the stars. The facts can rest now. The images can rest too. The moon over the ocean, the astronaut floating above Earth, the sun glowing from its deep center, the galaxy turning in the dark, the black hole holding its silence, the future unfolding slowly, far beyond the reach of any single night. And beneath all of it, beneath you, around you, through the whole long story, gravity remains calm. Softly holding, quietly gathering, almost politely keeping everything close enough to become beautiful.